Good morning, everyone. Welcome back to Physical Geology 1403. Before I get started, I wanted to show you some pictures that I promised a while ago I'd show you, and I simply haven't yet. Going up on that glacier over the summer in Alaska. This is up above Anchorage. No, Juneau. Sorry, Juneau. Huh?
That's in Alaska?
Yeah, this is Alaska.
Did you saw the lights?
The Northern Lights?
Yeah.
No, not while I was up there. No. I went in August. I think the best time to see the Northern Lights is May.
I want to go. I want to see them.
Yeah. And then this is me and the rest of the team that I went up with. It was fun.
And what were you excavating?
Wasn't excavating, just exploring. I picked up a few samples, looked down a few cracks, tried the water, you know. Everyone else was there as a tourist. I was the only scientist there. So they were all like, oh, it's so cold. I'm going to slip and fall. I was like, I'm going to go over there and look at those rocks. I went and clambered on a medial moraine for a little while. It was really fun. I had a blast. All right. Lecture 11. Before we jump into today's new stuff, any questions? No? We feeling good about Module 2 so far? This is the last lecture in Module 2. Next time we meet, we will have our exam review.
Yeah, so it's only like 2 classes we got on Module 2?
No, there have been 4 for mod. This is the 4th class in Module 2. Yeah.
It was short.
Yeah, there have been 4. Lectures 8, 9, 10, and 11 are Module 2. And then lectures 12 and 13 are Module 3. But the exam at the end of Module 3 is the cumulative final. It will cover everything. Any other questions about that?
When the metamorph rocks, how do we get them? Like, if they're near the magma.
How do we get metamorphic rocks?
Yeah.
You are correct that metamorphism occurs deep underground, but that's not always near magma, right? Only contact metamorphism occurs near magma. Every other kind of metamorphism happens simply as a product of the increasing temperature and pressure with depth. Now, you've already learned that there are processes that happen, tectonic processes, that can cause deep underground rocks to be pushed up near the surface, right? That's how we get metamorphic rocks up here. What else? Nothing? Okay. Well, then, I don't think I have any other announcements other than 1 week from tomorrow is our class movie night. So plan accordingly. If you need permission from parents to be here that late and you want to be here, please feel free to ask them sooner rather than later.
We can have an after party.
Do we what?
After party?
An after party? An after party after the party?
Yeah.
No, probably not. I will have at least one of my children with me, and we'll need to get them home.
After party at Aaron.
After party at Aaron's house. All right, you all heard it here. It's a bit far away. Where do you live? Out west, yeah.
And Aaron will buy the milk.
He'll buy the...
The juice, the orange.
Oh, good. The after party will have milk, guys.
An orange.
Okay, moving on. We good? Okay. Let's talk about shorelines. How many of you have ever been to the beach? Yeah? A couple of you. Highly recommend. Very cool. Awesome. Fun. But if you, what? Yeah, a few people here haven't. She's not the only one. Something that you'll notice if you've been to a beach over and over, the same beach over and over and over again, is that it changes a little bit as time goes on. What do we call it when natural things on Earth are changing? Dynamic, exactly. Shorelines are an excellent example of how dynamic Earth is. Let's see if my camera will follow me with a snake on my arm. You gonna recognize my, hello? You gonna follow me? Yeah, I can. I was just curious to see. All right, follow me over here. Maybe I don't like it if I did it this way.
You need a smarter camera.
Don't say that. I purposefully am nice to this camera just in case the robots ever try to take over the Earth. All right, how about now? And how about now? There it is. Okay. Sorry, Diablo, you were getting in the way of my hand. All right, where was I? Right, shorelines, extremely dynamic. What makes them so dynamic? Why are they changing all the time?
Sediment.
Right, it's basically just loose sediment. There is hard rock there, though, right? There are seaside cliffs, right? But why is it always changing? What is the mechanism driving that? Do you suppose? What water? The ocean, exactly. The largest mass of water on Earth is right there, right? And so it's constantly pounding into the shorelines, moving material, breaking material, carrying it away, constantly 24/7, 365, forever and ever and ever and ever. Hence why the shorelines are always changing, okay? So what we have here at the interface between the continent and the ocean are also intersections between continental processes and oceanic processes. The waves meeting with the sediment that has been weathered and moved to the shoreline. Okay, and so these two constantly, I guess you could say, battling different aspects of Earth make this a very dynamic interface here we call a shoreline. Now, naturally, some places will experience that erosion a lot faster than others. For example, I seriously doubt when these people built their houses or when these people built their houses, they knew they'd end up in this particular situation, right? 20 years ago, I'm sure that road looked just fine and these houses looked just fine. The ocean was probably way over here or even further. But because of how much material has been removed, this road is now just gone, and these communities are in danger. I don't know how much longer I'd want to live there. And it sucks because who's going to buy it? No one. Your bank's not going to back you, right? That's a bad investment now. You're just out a house. Hundreds of thousands of dollars in value before, just gone.
Beachside property, you know?
Beachside property. Beachside for the next 3 or 4 years. And then ocean property, right? Exotic, right. And then the same here. Who's going to invest in that? No one. Matter of fact, the only way that people can keep living in these houses, notice that they're built on stilts to keep the water from getting in the houses. They are built on stilts. That's not sustainable. Eventually, the water is going to keep pushing further and further back. And then how do you get to your house? Take a swim. Like park your car over here and swim to your house? Yeah, probably not, right? So this is something that is very relevant to a lot of people because a lot of people live near the ocean, okay? This isn't just an example of sea level rise. That's part of this. Like what we talked about last time, sea level rise, or at the time before that, I should say. It's not just a product of that. This is also because the shoreline is changing itself, okay? So before we talk more about shorelines and how they change, let's talk a little bit about what I mean by a shoreline. Okay, so the shoreline is that interface between the land and the sea, and there are a couple of parts. The shore, what we call the shore, goes from the coastline, which is the highest level that your water reaches during, say, a storm. Okay, that's your coastline right there. So if a storm rolls in, your water might push that far, but it doesn't go further than that. Okay. And then on the other end, we have the low tide mark. When the tide goes out, that's where the level of your water is. Okay, so between low tide and your coastline, this is what we typically refer to as the shore. Okay, now between the low tide mark and the high tide mark, right here, so the water goes back and forth between here and the tides, right? We call that the foreshore. Foreshore is between high and low tides. The backshore is above the high tide, but behind the coastline. So we have backshore, foreshore, and then behind the low tide, the part that's never exposed, that's called the near shore. And then way out deep ocean water, that's called offshore. So offshore, near shore, foreshore, backshore, and this is all the shoreline. That's what I'm talking about. This is what I'm referring to as a shoreline when, for the rest of today, I'm talking about how it changes. Clear?
For sure.
For sure. Good one. Okay. Okay. For those of you that have been to the beach, let me put this in a little more context, okay? You set your blanket and umbrella up on the back shore because you know the waves aren't going to get to it, right? But you go and you build your sand castles on the foreshore and you swim in the foreshore and nearshore areas. Okay. All right. Now, waves carry a lot of energy. They have, we'll talk in the next slide here about how waves start and what waves really are. But for now, just accept that they contain a lot of energy. When you are, again, for those of you that have been to the beach and can imagine this, when you are walking out into the surf, out into the ocean, and you're at knee height and a wave kind of comes and slaps at your legs, it doesn't really do much to you, does it? But then you walk deeper out and a wave of the same size, now that the water is chest height, what does the wave of the same size do? Kind of knocks you back a little bit, right? The energy in that wave, being equivalent to the first one, has not increased. So what has changed? Well, your balance is probably about the same. What has changed? Yeah. Huh? What? Not so much the level rise of the water. It has, but I mean, you're right, that has changed. But that's not what why are you getting knocked back further? Yeah. Huh? Center of mass. It's not center of mass. You are correct. It has to do with you, not the wave, though.
Is it because you're more submerged in the water?
No, not because you're more submerged. How much cross-section of my body is exposed to the energy of that wave at my knees versus my chest? There's more surface area of my body being impacted by that wave. I'm absorbing more energy, and so it is knocking me back further. Imagine how much energy from that wave is being expended along every surface of that shoreline. Wave after wave after wave after wave constantly. That's a lot of energy crashing onto the sediment or the rock or whatever our shoreline is made out of. So yeah, it's going to gradually pulverize down whatever material that shoreline is made out of and carry it away. Waves come in, waves go out. Waves come in, waves go out, right? It carries stuff away. Some waves, the larger waves that crash onto shorelines in some places, can have as much as 10,000 kilograms of pressure per square meter. Okay? It's a lot of pressure. Constantly grinding, crushing, impacting. Now, that's not the only thing at play here. Because these waves have energy, they probably are also carrying what in them? Sediment. Suspended load. They're bringing sand, or in the case of higher energy waves, maybe even gravel-sized pieces. And those pieces are going to crash and crunch and slam into your shoreline. breaking things apart even further, making finer and finer sediment pieces. Okay, that's abrasion, wave abrasion. Remember, all these rocks are going to gradually lose their corners and their sharp edges and get rounder and rounder, right? As more weathering happens to them. Okay? It's because of this process. They are getting abraded against other particles. They are weathering each other.
Abraded. Abraded.
Abraded.
I like
Yep.
that word.
There are some nice terms for that word and other not so nice terms for that word. I'm thinking of medical abrasion. That's not fun at all. Don't Google that. All right. Or do if you want nightmares. Okay. Let's talk about how waves are formed and about how they move. Okay. So many of us think of waves in terms of being water that moves across the ocean, right? You've got a wave, it's formed somewhere in the ocean, it moves across the ocean and slams into California coastline, right? Or Hawaii, or Japan, or Thailand, or whatever, right? That's not exactly how it works, though. What forms our waves is actually energy from wind. Okay, a principal wave forming mechanism is energy given to the water by the wind. I'll use purple here because you can see it better. So, wind is blowing that way, okay, which means that it is giving energy to the particles on the top of the water in that direction. And they move in that direction. They make a cycle like so. These top particles of water are moving like this. As they do so, some of that energy is given to the particles beneath them. Not as much of it. And then again, like so. And then again, and then again. Diminishing returns every time until finally you reach a depth at which little to no energy is passed along. Okay? Call that wave base. Okay? Below that point, there is no water movement due to the energy of the wave. It varies. It depends. How large your body of water is, how strong your wind is, right? This process, the stronger your wind, the larger your waves will be, and therefore the deeper they will go, right? There are a lot of factors that are involved in how deep that wave base is, okay? Now, think of these as, well, a sine wave, right? We've got our crests and our trough. Y'all are familiar with sine waves. Feel free to groan as much as you want that I'm bringing math into this. We're not doing any math. I'm just using this as an example, okay? You're all familiar with the concept of a wavelength and a frequency and all of that. Well, right here, between our wave crests, that's our wavelength, right? And this right here, remember what we call that? The height of these waves? No. I mean, the apex is your crest, right?
Wavelength?
No, the wavelength is this. That's okay. We'll get to that. Now, where's my cloth? Sorry, I promised I wouldn't give you guys that much math. But we're talking about waves, not sine waves, right? Now, all of these factors are dependent upon where the energy is coming from, aka the wind, how strong it is, so on and so forth. But what happens here is that our water isn't really moving. The energy in it is. And so the energy is cycling through water. Wherever you see the crest of a wave, that's where that sort of column, that pillar of rotating energy is. And that energy is moving across the ocean, not that water. Which is why when a boat is sitting on the ocean, it bobs up and down with the waves instead of being carried all the way to California from Japan, right? Or from Hawaii. It just bobs up and down in the waves because the energy is moving, not the water itself. There's a little bit of water movement. I won't say that there's not. But most of that movement is because that column of energy is getting pushed through the ocean. Where there is a trough, no column. Crest, column of energy. So what happens eventually is your column of energy moves across the ocean until finally it gets near shore. What happens when the bottom of our wave, that right there, that energy level, what happens when it hits the rising sea floor as it approaches a continent? It starts to pick up sediment, true. It doesn't get compacted.
Smaller but stronger.
It starts to expend energy on that, right? And as it starts losing energy at the bottom, but the energy on the top is still going strong, our wave tips over. And that's what makes those white crests that you see on the beach. In the ocean, you've got these nice rolling waves, but when you get close to the beach, they kind of tip over and form those white crests, right? Perfect for surfing. It's because of this. They've run into the near shore and are tipping over as the energy on the top is moving faster than the column is at the bottom, until finally it falls flat on its face on the shoreline. That's how waves work. Any questions about that? No? Okay. Now, as these waves are moving in and out from the shoreline, they are doing something to the sediment there. They are moving it, picking it up, carrying it away, depositing it again, picking it up, carrying it away, depositing it again, back and forth, back and forth, back and forth. This creates something that we call the longshore current, okay? It's very rare for waves to be exactly parallel to the shoreline. Think about how many angles there are on the shorelines around every continent in the world. What's the statistical likelihood that any of those shorelines is exactly parallel to the way direction the waves are coming in? Very low. There are some where it's true, but very few. Most of those beaches, most of those shorelines are at angles, some at some perpendicularity to the approaching waves. And so, like you see here, right? Where they're hitting the beach at an angle like that. So when our waves impact the shoreline, they are going to push the water and the sediment they are carrying up onto that shoreline at the angle that they impacted at. Okay? But then, once that wave has gone all the way up the shoreline and it slows down and it stops, it no longer has that wave energy. What happens then? Does it stay there? No. It comes back down the shoreline. And what is it that gives energy to things going down?
Gravity.
Gravity. What direction does gravity like?
Down.
The easiest way it can go, usually about 90 degrees to the slope. Okay? So the easiest path that gravity pushes that water back down is not in the same angle it came in. It's at 90 degrees to that slope, where that water and all the sediment it's carrying with it comes back to the ocean, gets picked back up by the next wave, and shoved back up at that same angle that it was before. And so we get this migration of both water and sediment moving up and down the beach face. And we call that the longshore current. That's why when you set your beach chair up, you're under your umbrella, you got your book, and you notice that someone left a styrofoam cup in the water, you're like, oh, that's a shame. I should go pick that up. And when I finish this chapter, I'll go get it. And then you finish your chapter and you look and you're like, the cup's gone. How'd it get down there? Longshore current. In, out, slowly making its way down the beach. Okay? Cool.
I would never have that good of luck. There's usually always a typhoon going on whenever I get.
You would never
beach.
what?
I would never have that kind of luck. There's usually always a typhoon going on.
A typhoon?
Every time I go to the beach, it's always, oh, there's a typhoon going on. I'm like, ah.
I've lived through hurricanes in Louisiana, and typhoons in Japan. And there were a couple of bad storms in Hawaii, but none nearly as bad as the typhoons in Japan. That was brutal. I'll talk more about that later on. We'll actually talk about hurricanes and other storms like that here later on in the lecture. Okay. Now, some of the effects that this wave action can have on the shoreline, okay? Some of these features that we typically will see as a product of these mechanisms. Wave cut features, okay? So what will happen here is because your energy is restricted in that wave column, it's going to be giving some of that energy and therefore removing some material a little at a time at any rock within that column level. Anything below the level of that wave column doesn't really get broken down as fast. And so what you'll often see, and well, I can't say often, what you will sometimes see is there is some platform of rock underneath the waves. You're seeing it at low tide. Under high tide, you wouldn't really be able to see this. But at high tide, this doesn't get weathered at all. Sure, it does at low tide, but not during high. And so we've got this sort of platform out here. And this is where our actual shoreline is, right here, that interface. This cliffside, constantly being weathered and broken down by the waves that impact it. Now, what will happen is some tectonic activity will cause this to get pushed up. And when it does, what once was our platform will become our new marine terrace, and the shoreline will be back here. Okay, so once this all gets pushed up, this becomes that, and this just gets pushed up higher. Okay. Sea arches like this will form when, for a couple of reasons, there could be some kind of weakness in the geologic structure of this cliff that caused this material to fall down, break down faster. Or perhaps as a product of the longshore current, more wave activity was pressed into that particular part of the cliff. It slammed into that more and more and more until it weathered down faster than the material on each side of it. Either way, that's a sea arch. Now, when your sea arch, the top of your sea arch collapses, because imagine this is going to keep growing bigger and bigger and bigger until what happens? Gravity forces this to fall down. What do we call it when gravity forces material down? Because of a loss of support? Mass wasting, thank you. When the support is gone and gravity does its thing on that rock, it will fall down into the ocean, leaving behind just this side of the support structure, making kind of a little island pillar out there. That's called a sea stack. Here's one right here. Okay, that's a sea stack. That will be a sea stack when the top of the arch collapses.
It happened where I come from. It happened once because of earthquake.
Yeah, earthquakes will do that.
It broke it.
Yeah.
And it was famous.
Yeah.
And it broke.
Yeah, happens all the time. Okay, barrier islands. Who can tell me where this is, by the way?
Bahamas.
Not the Bahamas.
Whoa.
Huh?
Whoa. Something I've ever seen on a map before.
Something you've never seen on a map before?
Australia.
I'm going to let you think about it for a minute. Meanwhile, what do we see out here? Well, we've got a couple of islands out here, and then we've got this weird spit shape like this. What's happening here? The waves, as they are approaching the shoreline, are picking up sand, that nearshore sand, and pushing it closer to the shoreline itself. When a storm rolls in, the storm wave base, the energy column for those waves is significantly deeper and stronger. And so it can pick up more sand and bring it closer to shore. And so every time, let's say, hold on, let's say that this is our shoreline right here. There's our sea level. If this is our typical wave base, right? A storm wave base is going to be more significant. And so it's going to pick up more and more sand and push it further and further. And every time there's a new storm, it's going to push more sand, and it's going to push more sand and more sand and more sand until finally you get a pile of sand that has made an island. We call these barrier islands. These are barrier islands. This is a spit made through the same process, plus longshore current pushing sand out here this way, protecting this bay, by the way. Okay? This is how barrier islands form. If any of you have ever been down to Corpus Christi, Padre Island, those long sandy islands that are out in front of the Texas coastline along the Gulf of Mexico, those are barrier islands built through this process. Storm pushed sand and made those islands. Now, let's get back to where this is. Massachusetts. This is Massachusetts. This is Cape Cod. I'm assuming none of y'all have ever been there. I cannot recommend it enough. I love this place. This is this is Cape Cod. Okay, this is Gloucester Bay. There's Gloucester. The town of Gloucester is out here. Any of you all like clam chowder?
No.
I love clam chowder. It is so good. And if you want the best clam chowder of your life, you just go to Gloucester and you walk along the shore, and there are these little, they're restaurants, but they look like people's houses. They probably are people's houses, and they just have like a restaurant on the bottom level. But they have the freshest seafood you will ever eat. This, ever since settlers arrived here, and before that, Native American populations knew that this had some of the best fishing anywhere. Okay, this is protected from storm activity. It's perfect. Some of the best fishing in the world has been in there for centuries because it's protected from the ocean. Okay, but anyways, yeah, best clam chowder of your life, or any kind of chowder. They have all sorts of chowder: fish chowder, clam chowder. It's delicious. It's amazing, and I want some right now if I can. Someday I'll take my wife. She's never been there. I'm going to take my wife, and we're gonna do that. Huh? Let's make a trip. Class trip to Gloucester. Who's in? Cool, cool. Y'all have to pay for yourself, but yeah. All right. But yeah. By the way, this weird feature here, this is a moraine. This is a glacial moraine. Yeah, during a past ice age, a glacier made it all the way out here, dumped a bunch of sediment in a moraine. And that's what this is. Okay? That's all. The core of this chunk of Massachusetts is glacial rock. And then it's had a whole bunch of sand pushed on top of it by the wave activity.
So it's actually red?
It's what?
Red?
No. Good question. Why are these pictures red? Because when you take a satellite image, you can choose to put a filter on that image that shows vegetation. What you're looking at here, everywhere that's red, that's actually green in real life. Okay, it's green, it's plants. Okay, we just sometimes we'll put a red filter on it to really make it stand out better than the green would, especially against, you know, dark blue of the ocean right there. Okay, where are you going, kiddo? Wherever you want. Got it. All right, so we have determined today that shorelines change a lot, and that can impact human populations quite a bit. We've seen a few examples of that. Okay, there must be some way that we can stop that, right? That we can help those populations of people not be so affected by shoreline change. Well, we can't really stop it, really. The ocean is a force that is titanically powerful. Words chosen very carefully there. Thank you. Okay. There are ways that we can slow it down, though. Let me share a few with you. Jetties. Jetties are walls that we can build out perpendicular to the shoreline and to the longshore current, right? That are used to protect waterways, canals, river outlets, bays, stuff like that. Why do we do that? Because otherwise the longshore current could potentially gum it up, right? Fill in that outlet with so much sediment that you can't get ships in and out. Okay? Hey, dude. So we build these jetties out to capture the sediment from the longshore current. Now, as you can see from this picture down here, eventually that stops working so well. This jetty has filled in behind it with so much sand that the sand is built up and is now once again threatening that waterway. Now, what happens when that occurs? What are your options? You could make the jetty longer. However, the water is deeper. And so pushing your jetty out further has to go deeper because you're basically sinking it into the ocean bottom, right? So it's enormously expensive to do that. And what does that do except build up more sand until the next time it builds up, right? You're buying time. What are some other things?
Excavate.
What?
Excavate the sand.
Excavate the sand. Yes, actually. We call that dredging. Removing that sediment and taking it somewhere else. There may be some places that desperately need sand because theirs are being carried away. I'll show you an example here in a minute. But you take that sand, or maybe you just dump it over here. Look, there's no beaches over here. Maybe you just dump it on that side, and it just makes its way further down. Or you take it out into the deep ocean. Or you take it inland and use it as for concrete or something. But regardless, you can dredge that sediment away. So there are ways that we can extend the lifespan of these jetties. But eventually, nature is more powerful and patient than humanity, is a theme that you'll see, right? Not only in this lecture, but hopefully in a lot of others that we've had and will have. And so eventually, nature wins, regardless of what we can do. Groins are essentially the same thing as jetties, walls that we build out perpendicular to the shoreline to slow down longshore current. But they also suffer the same fate. Eventually, they will fill in. You can see how each particular groin section has sediment starting to fill it in. Eventually, that is going to build its way out, right? What is this meant to do, though? This has a slightly different result.
Keep it there.
Yeah. What do we have here?
Houses.
Houses. If we had not stopped that longshore current from stripping away sediment, what would be the eventual result? The shoreline continues to move that way until it gets into those houses. Exactly. So, build out groins to protect these communities. And then there are breakwaters. A breakwater is essentially a chain of artificial islands that you build out. Is that your hand up? No? Okay. A chain of artificial islands that you build out to absorb the energy of those waves before it even makes it to the shoreline. You'll typically build a breakwater in front of some infrastructure you want to protect, a military base or a ship anchorage, or maybe the front of a river or something like that, where you really don't want the energy of those waves to come and impact your shoreline or whatever is in front of your shoreline, okay? So these are basically, let me do this with my left hand because I got Mr. Man here, okay? Plastic islands filled with air so that they float, chained to the ocean floor. Now, that's my water level. What happens when my wave runs into that?
It goes back.
I mean, yeah, this is going to rock back a little bit,
No,
but why?
The energy.
The energy, it's going to reflect off? No, it's going to be absorbed. And so your wave just dies there. You take the energy out of the top of the wave, the bottom of the wave just kind of disperses. Okay? That's what these breakwaters are meant to do.
Break water.
Break the water. They absorb the energy of the wave. Now, what happens if we don't do any of these things? Or if we do them too late? Or if it's not enough? Well, eventually, you lose your sediment. Your shoreline changes in ways that may not be particularly beneficial. Okay? For example, Florida. People go to the beach in Florida all the time. It's like Florida's big thing, that and Disney World, right? You go to Florida for Disney World or for the beaches or retirement communities. I think Florida probably has a reputation for having a lot of retired people, right? Probably because they don't like the cold. But what happens if you don't protect your beach sand and longshore current does its thing? To communities in Florida where their beaches give them so much tourism, that's bad because eventually you end up with not much of a beach, right? You can see they built groins out there, but not quite in enough time. So what do you do when that happens?
You put sand.
You have to put sand back. Otherwise, just give up on the whole beach thing, right? Where does that sand come from?
Where there's too much.
Yeah, maybe one of those other places where they have too much. Where did all that sand go? It must have gone down the beach somewhere, down that longshore current. Maybe they don't want that sand, and so you come and put it back. Now, eventually, it is eventually going to make its way back down. True. This is called beach nourishment. Occasionally, you need to dump sand in places where you want your shoreline to remain the same. Okay? So depending on the situation, we may remove sand because it's not good for us. And in some places, we may add sand because it is good for us. All right. Now let's talk about hurricanes. How many of y'all have ever been in a hurricane? You have. I have. They are very powerful. Hurricanes change shorelines. As a matter of fact, in Louisiana, every time there's a major hurricane, they have to remap the entire coastline of Louisiana because there are some islands that will be gone and some new ones that will be there. And to protect shipping lanes, they need to make sure that they know exactly where all these things are. Okay, so the coastline protection agencies in Louisiana, they pay special attention every time there's a hurricane. They go out there and they check everything to make sure it's the same. And if it's not the same, they map it and get depth charts so that they can keep their mercantile industry safe and the private citizens as well that take their boats out there. Now, more than 50% of the population of the United States lives on or near a coastline. Okay? That's a lot of people that can be affected by massive storms like hurricanes. Matter of fact, when I was living in Ohio as a kid, when I was 17, we had a hurricane that made it all the way up from Florida to Ohio. And it flooded out my community. I had 3 feet of water on my street. I remember putting on my swimming trunks, going and swimming with my brothers and sisters until my dad ran out and grabbed us and pulled us back in the house because he didn't want us to get sucked down a sewer drain. The sewer drains had kind of turned into these whirlpools, which we thought were cool, but definitely could have killed us, especially my younger siblings. We didn't really think it through. Regardless, these hurricanes have a few factors that make them deadly to human populations and give them the power that they need to change the coastlines as drastically as they do. Okay. Storm surge. Y'all ever heard of a storm surge? No? Okay. A storm surge is often described as a wave that accompanies the front of a hurricane. As your hurricane is approaching land, they will often say there is a 4-foot storm surge that will accompany this hurricane. Okay, doesn't really mean anything to you and I here. Coastal communities care about it more. But a storm surge is not a wave. Remember that a wave is a part of water, okay, that is currently up above the rest of the water because it is transporting energy, right? Or there is energy in that water at that time. Storm surges are different. A hurricane is formed because a low pressure and high pressure front have basically intersected each other, okay? In the middle of your hurricane is an extremely low pressure zone. We call that the eye, okay? The eye of your hurricane has extremely low pressure. So if there's my shore, there's my ocean, there's my hurricane, in the middle of my hurricane is the eye. The ocean inside of the perimeter of that eye under less pressure is going to be higher than the level of the ocean around it. There isn't as much air pressure on it. And so it's going to be slightly elevated above the rest of the ocean around it. That's a storm surge. Now, what does that mean for people on land? Well, what happens when that storm surge, reaches land? It's going to wash over the land, following the passage of that eye as it moves out over land. Some of these storm surges are almost 20 feet tall. And that is deadly if you're less than 20 feet above sea level, right? Or at least extraordinarily destructive. Look at how much of all of this has been stripped away. Trees, houses. These are all concrete pads. Those are foundations. The houses are gone. The foundations are there. The houses are gone because they got destroyed by the storm surge and then stripped away when the storm surge went back out to sea. Yeah, hurricanes are extremely powerful. That's just a storm surge. Then you got the wind. Category 5 hurricanes have 250 kilometer per hour winds. That's enough to turn your vehicles over. That's enough to rip houses apart. Could carry you away, right? Then there's the rain causing all the flooding. Wherever the storm surge doesn't flood, the rain will, like I just said, in my community in Ohio, right? And that was after the hurricane had died down for a bit. Hurricanes, typhoons, and cyclones. Those are names given to these storms. They are all actually the same kind of storm. They just have different names based upon where they are in the world, okay? They tend to be called typhoons in this part of the world, and then hurricanes over here and over here, and cyclones as well. That's kind of a, cyclone is more of a Jamaican name. I believe it has Jamaican roots, okay? But they're all the same storm, okay? Just in different parts of the world. Hurricane Katrina. You all ever heard about that? Massive devastation from there. Communities are still recovering from Katrina in some parts of the South. And then they just keep getting hammered over and over by more and more hurricane. Any questions about that? Great. Now, some coastlines are rising and some are falling. Why? Well, rising coastlines where you are gaining more land, okay, an emerging coastline it's called, that happens when tectonics is such that your continent is rising higher than the elevation of the ocean, okay? There are some places in California where that's happening. And then you've got submergent coastlines. That's where the ocean is gaining on the land. There is less land because it is constantly being incorporated into the ocean. Now, if you ignore rising sea levels as our current trend in our global warming process, that is still happening in some places if you just ignore that one fact, okay? For example, on the East Coast. You'll see this. Where is that? This one's easier. It has a name on it. It has a bunch of names on it. This is Chesapeake Bay. Here's Virginia, Maryland, Delaware, New Jersey. Chesapeake Bay. That's ocean. Does it look like anything to you, though? What does the shape remind you of?
River.
A river. And it should. That used to be a river. This all used to be a river flowing down into the ocean down here. But now, the ocean has invaded that river all the way up. Why?
The entrance is too open.
Because this part of our country is slowly submerging under the ocean, sinking, a little bit at a time. Sea level rise is only increasing the rate, but that coastline was already sinking a little bit, which is why once the elevation of that river was beneath the elevation of the ocean was able to come in and fill in that river. Okay. Another word for that is an estuary, a drowned river. Now, how can we tell whether or not a location in the world was above or below sea level historically, looking at the geologic record? What have you learned so far already that can help you figure out if a place in the world was above or below sea level?
The fossils.
Fossils, good, but the fossils are in
The rock.
rock. Rock is your first tip. If it's a limestone, under sea level, right? If it's a shale, probably under sea level. If it's a sandstone, it could be on the shoreline or in a desert, right? But the type of rock is the first indicator. Fossils, yes, those come next. Those are also fantastic indicators. But the study of the sequence of rocks to determine something like where sea level was at that point in time, we call that stratigraphy. And the sequence of rocks tells us sea level was rising during this time period or falling during this time period, or rising or falling. This is an emerging coastline or a submerging coastline, all of that. If I were to drill a hole right here, I would see limestone on top of shale. To me, that says rising sea level. Why? Because the deep ocean rock was on top of the near ocean rock, right? If I were to drill right here and say, well, I mean, that's just the same thing, right? Thick limestone on top of shale, that just means it's even deeper, right? This has just kept on going. Transgression, we call that. Transgression is when sea level is rising, okay, over land. Transgression, sea level rise. Regression is sea level fall. So I will see near shore sediment on top of deep ocean sediment. Like this. I see sandstone on top of shale on top of limestone. Regression. But then underneath of that, limestone on top of shale on top of limestone, or on top of sand. That's transgression. So if I were to drill a core right here and analyze the sequence of rocks, I would see a transgressive sequence underneath a regressive sequence. To me, that would say oceans getting deeper and invading on top of land, and then something changed in the environment, and now oceans getting shallower, retreating from land. Transgression and regression. Okay. Let's talk about the tides for a minute. Tides are caused by what? The moon. Exactly. Wherever the moon is, as it circles our planet, there is a bulge of water on that side of our planet and on the opposite side, by the way. Okay. High tide, we call that bulge. Water on the ocean temporarily gets a little bit higher wherever the moon is and on the opposite side of the world from that. Okay. So there's always high tide in two places. Okay. This is why it's so easy for us to predict where high tide will be and when it will be. If you've ever gone and looked at like those sailors' almanacs or anything like that, they'll tell you exactly down to the minute when high tide will start and when it will end, and then low tide and all of that. How do we know that? Because it's easy for us to chart the path of the moon. Okay. Wherever you have a place that is only flooded during high tide, we call that a lagoon. Okay. And when the water is not present, so during low tide, we call that a tidal flat. It is periodically exposed to the atmosphere when low tide is happening. There are some very cool ecosystems that exist in tidal flats. Organisms that can survive both atmospheric exposure and in the water. Take 1404 and you'll learn more about those organisms because they tend to be pretty important. The things that live in those ecosystems are usually the ones that have been around for a long time. Give y'all a second to catch up there. Okay. Let's talk about the ocean floor. Back in the late 1800s, there was a ship called the Challenger. The Voyager was a different ship. The Challenger was dispatched with a mission to chart the depth of the ocean. How do you think they did that? With a rope. They took some rope, they tied a weight on the end, and then every 6 feet, they had a knot. And so you throw your rope over the side and count how many knots go over the side after it until your weight stops, which means that it hit the bottom. And then you do the math. Okay, 29 knots went over. There are 6 feet between each knot. Figure out how many feet of depth that is, right? That worked until they reached oceans, or like ocean depths that were deeper than their knots could go. They didn't bring enough rope. They had to get more rope, and they were like, oh man, ocean's a lot deeper than we thought. Everyone thought that the ocean was only a couple 100 feet deep until the Challenger went and did this particular experiment. And then they understood, shoot, we're talking thousands of feet deep. In some places, miles deep. And that opened up everyone's eyes to exactly how massive, how unknown the ocean depths were. And that made everyone start to be like, that's kind of where our whole fascination / fear with what could be in the ocean. I mean, it's not where it started, but it sure didn't help that, right? Nowadays, we have new modern ways of determining what the depth of the ocean is. By the way, the study of ocean depth, that's called bathymetry, okay? How do we do bathymetry today? We have something called sonar. Sound, navigation, and ranging. That's what that stands for. You ever watch those military movies with the submarines and they do the ping? They are sending out a sound wave into the water. When that sound wave interacts with an object, some of it bounces back at the sender. The amount of time that it takes for that sound wave to return tells you how far away the object is. You know the speed of that sound as it goes through the water and as it returns, which means if I know the rate that it moves and the time that it came back to me at, I can get a distance out of that. That's how sonar works. Now, for you and me, we're going to actually take that concept a little bit deeper, okay? We're also going to use, or we're going to learn that you can use the wavelength that returns to you to figure out what material it bounced off of. Very interesting. But for now, we just use the fact that it returns and how long it took to return to figure out distance, which means that I can send a wave out from a boat on the surface of the ocean towards the ocean floor, and the amount of time that it takes to return to me, that tells me how deep the ocean floor is at that location. That's how we use sonar to do bathymetry today. No more ropes, right? That's how we know how deep everything is. Now, a seismic profile. This is using that concept. Send out a sound wave, it comes back to you. However, the wavelengths that are returned to you, and frequencies, by the way, are going to be indicative of the material that it bounced off of. Some materials will absorb certain wavelengths and frequencies, and other materials will absorb other wavelengths and frequencies. And so in a controlled environment like a lab, I can test what materials absorb what. Which means that if I send that sound wave to the ocean bottom and it returns to me, I not only know depth now, but based on the wavelength and frequencies that returned, I know what the material is at the bottom as well. Now, it goes even more than that, because some wavelengths and frequencies can penetrate rock. And as they penetrate that rock and they encounter a new layer of rock, they are also in turn going to be bounced back up to me. And so that's how we make what are called the seismic profiles. I have a sneeze. I'm trying to fight it. Thank you. Appreciate that. Okay, a seismic profile looks like this. It just looks like a whole bunch of static noise. You can kind of see that there are some lines in there, right? Those lines represent different types of rock. And we can generate a profile like this simply based on the wavelengths that are bounced back up to us, the time that it took for them to return to us, and what wavelength and frequency they are. We can unravel all that and put together something like this. And then after some time, it used to be that people would do this, but now computers are getting better at doing it. You can generate a model like this, where you can say, this is that age rock, this is that age rock, this is that age rock, this is limestone, this is shale, this is slate, this is sandstone, right? Very, very useful for, say, the oil industry, and you want to know what you have under the ground before you spend millions of dollars to drill something there, right? Also for finding water. Okay. Now, the ocean floor is kind of split into three provinces, we call them. Continental margins, which are obviously the parts near continents. The deep ocean basins, which are obviously the parts that are far from continents. And then your mid-ocean ridges, which is where plates are spreading apart from each other, those divergent plate boundaries. Continental margins are divided into passive margins and active margins. Along passive margins, think east coast of North America. There is sediment building up along the edge of your continent. There is no tectonic collision. There's nothing tectonic really at all, except your sediment is getting deeper and your continent is usually settling deeper as well, which is why the East Coast is currently submerging. Okay, not a whole lot going on there. Your continental shelf, your slope, and your rise are the different sections. So your continental shelf, think of that as flooded continental rock. Currently, right now, because we are not in an ice age, the world is not covered in glaciers. that is not exposed. There's enough, I don't want to say extra, but more water in the ocean now that this section of continent is flooded. Okay, that's your continental shelf. This slope is called the continental slope. I know, imagine that. That's your transition going out into deeper water, and then the continental rise, that is oceanic rock that is slightly going up into the slope. So you go rise at a gentle incline to slope, more steep incline, and then your shelf before you reach land. Okay. Along active margins, it looks a little different. An active margin is, when I mean active, I mean tectonically active. Usually this means convergent plate boundary. Okay? So one plate sliding under another plate. What that does is where your thinner, denser plate is sliding under your thicker, less dense plate, you're going to end up with a trench. Think of that as the location where your thinner plate is diving under the other plate. Okay, it is bent down, and there is now a gap. Not quite a gap, more like I don't know a good way to explain it. Where you have two things, one that is at this angle, and one that's at another. You can see that there is this triangular kind of divot between the two materials, right? Between my fingers. Okay, maybe you can't see that, but if you do it with your own fingers, you could probably be able to see it. Hey, Diablo sees it. But that's a trench. There is a buildup of material right here in that trench. Where is that material coming from? That's all the loose sediment and rock on the top of your continent, on the top of your oceanic plate that is getting scraped up onto the edge, the leading edge of your continental plate, your overriding plate. As this plate dives underneath of this one, all that loose stuff on its surface gets scraped up onto the edge of your overriding plate and makes that accretionary wedge. So between your accretionary wedge and your descending plate, you have a trench. And some of these trenches are extremely deep. Okay. Our deep ocean basins are, there's a lot of them, okay? About 30% of the Earth's surface is covered in a deep ocean basin. Makes sense. Look at how much of our Earth is covered in water, right? Substantial amount of that is going to be deep ocean. These are usually pretty flat, generally boring, except for maybe seamounts, trenches, and the occasional shipwreck, okay? Trenches. The deepest trench in the world is the Mariana Trench, 36,000 feet deep. That's deep enough that if you took a little submarine down there and something bad happened, you'd quickly find your submarine compressed to about the size of a basketball. Yeah. How many of you heard about the tragedy that happened at the Titanic not long ago? Yeah.
They found the wreckage.
Found the wreckage. Something happened. Pressure seal was violated somehow. They imploded. When the submarine imploded, the people imploded. Not pleasant to think about.
Well, they didn't feel it either.
It was instantaneous.
Yeah.
No, it was instantaneous. Which is small comfort, right? That's why we have to be extremely careful, and why these devices that go down into the Mariana Trench are extraordinarily expensive. Opposite problem of going in space, right? In space, you're trying to keep your pressure in a low pressure environment. In going down in the deep ocean, you're trying to keep the pressure out and keep living in your low pressure environment, right? Both have different set of challenges. Some of the physics are relatable, but not entirely. Now, there are some very large trenches that we have. The Mariana Trench is right here, south of Japan, east of the Philippines. Okay, this is your Mariana Trench. Japan Trench, Corrido Trench, Aleutian Trench, Central American Trench, Peru-Chile Trench, Tonga Trench. Do you notice what all these trenches have in common? What are they around?
An island, continent, like a land.
The coast, they're on the coast, but surrounding this Pacific plate, right? They're on the Pacific Ring of Fire. These accompany converging plate boundaries, right? Which we already established a while ago, happen all around the Pacific Ring of Fire. That's why we have a lot of volcanoes, hence the name Pacific Ring of Fire, right? All right, abyssal plains, that's those just boring nothing areas deep out in the ocean. Not a whole lot going on there. Seamounts, there are lots of seamounts. We have found more than 1 million seamounts on the ocean floor. It's more likely that there's closer to 2 million. We cannot watch all of them. There are far too many for us to monitor. And occasionally, because we can't do that, they catch us by surprise and do something ugly, like what happened to Tonga about 1.5 years back. Okay, seamount about 5 miles, I believe it was, from the island of Tonga, went off, and tsunami flooded the capital. The island was covered in ash, had a whole thing, but they didn't see it coming really because no one was watching the seamount. There are far too many for us to keep track of. A plateau is where a lot of lava has been expelled at the bottom of the ocean and has kind of made a region at the bottom of the ocean, a region of volcanic rock that is elevated above the rest of the rock because so much magma was spit out on the surface. So if I show you this map right here, take a look at this. You see this white area around New Zealand right here? That shows you that the deeper the blue is, the deeper the water. The lighter the blue is, the shallower the water. That shows you there's a significantly large chunk right here of ocean floor that is above the rest of the ocean floor around it. That's a basalt plateau. Let's see, we've got more down here. We've got more right there, okay? Those basalt plateaus down at the bottom of the ocean where a lot of lava was spit out. Now, this map is also showing you mid-ocean ridges. Specifically, they are color-coded to show you how quickly those ridges are splitting apart, okay? The East Pacific Rise, right here. This is a divergent plate boundary. There is a lot of movement right there, okay? Pushing the Cocos Plate here further underneath the South American plate, okay? This is the Mid-Atlantic Ridge right here. That's where it splits Iceland, right? I showed you that picture of me on that boundary earlier in the class, first day of class, okay? Now, at these mid-ocean ridges, let's look at a cutaway of them. As they are starting to form, you basically just have ocean crust that starts getting thinner and faulted as the convection is underneath of it, starting that opposite cycle cell motion, doing this underneath of the plate. As it does this, the drag on the plate above it in 2 different directions starts to stretch and thin and crack and fault that plate until finally you end up with so many faults that the lava, the magma can make its way up, become lava, right? Get expelled. And now you have convection doing this underneath your plate, pushing them apart, thinning it there. Magma comes up, adds to both sides of the plate, and that's how you get your divergent plate boundary. If I was to look at a cross-section of the ocean crust, it would look something like this. Here we have mantle, okay, so that's not the crust, but above it, we've got some gabbro, where the gabbro is really tightly compressed up against between the mantle and everything above it. It would probably be kind of a layered gabbro. You might confuse that with gneiss, but it's lacking those light silicates, right? And then we've got just normal gabbro above that, intrusive igneous rock, mafic, right? Above that, we have Dikes, vertical shafts where magma made its way up at the mid-ocean ridge. Okay, these vertical shafts that were conduits for the magma and have now been shoved off to the side because they are no longer at the mid-ocean ridge. They've been shoved off to the side, but there's this layer of dikes. On top of that layer of dikes, basalt lava flows of whatever the dikes brought up, okay? So there's your lava flows. Above that, that's where you got your sediment, the shales, the limestones. If you're nearer the ocean, sandstones, right? Okay, and then you've got your water up there. Okay, so this is a cross-section cutaway of the ocean floor, the ocean crust. Any questions about that? Okay. I've mentioned these before. This is called a black smoker. When water makes its way down through those faults at the mid-ocean ridges, it tends to engage in some metamorphism activity there. It pulls metals away from those forming silicate minerals, making new metamorphic minerals, right? Like our talc schists and whatnot. And then those metals in that super hot boiling water get expelled out of the crust and make these black smokers. And that metal kind of falls down all around, collects. It is believed that these are the locations where the first chemosynthetic organisms developed. We'll talk more about that in 1404. Okay. But those are a consequence, a direct consequence of this divergent plate activity of those mid-ocean ridges of the activity happening there. Okay. Oh, yes, rift systems. Okay, so right now in Africa, there is what we call the East African Rift Valley. It goes right here. And if you look at any map of Africa, you can see the chain of mountains, volcanoes, deep valleys, and lakes along that valley that indicate what I'm about to tell you. There is a relatively new, when I say new, I'm talking like, 40, 50 million year old. Okay? You okay? Oh man, I'm sorry. There is a new divergent boundary starting here. It started there a while ago, but we can see it manifesting on the surface. The plate, the African plate is being pulled apart in different directions here. This section of the plate is thinning, faulting, cracking, allowing for more volcanoes to form. Magma makes its way to the surface, you get volcanoes. As it continues to fault and thin and crack, eventually those volcanoes are going to stop being felsic and intermediate volcanoes. And because it is closer to the mantle, because of the thinning of the crust here, there's going to be more mafic magma coming out. More mafic lava is going to be deposited. Mafic lava, denser, makes denser rock. Oceanic crust is thinner and denser than continental rock. And so because we are going to start forming thinner, denser crust here, the ocean is going to invade, and you're going to end up with a shallow sea between what will be called West Africa and East Africa. Cool?
How much? How much?
Well, there will probably be a stretch of sea, very similar to what you see in the Red Sea right there. There'll probably be something about that size there in the next 20 to 25 million years. Mm-hmm. Soon, yeah. Geologically speaking, soon. Yes. Now, here's a fun thing. This is happening in the United States, too. The Rio Grande Rift Valley, where our own Rio Grande River currently runs, is also splitting apart. Give it another 20, 25 million years. There will be an extension of the Gulf of Mexico running up into North America where the Rio Grande River is right now. At least we believe so.
So another
Another what? Another civil war?
When it gets separated?
In 20 to 25 million years, I'm hoping we will have ascended things like war.
We probably won't be here. Maybe.
I won't be here,
I hope we won't either.
right? Any questions about any of that today? No? Okay, well, that's it for lecture. I'm going to go ahead and give you some instruction on Lab 5 now. Hey, you came back just in time. All right. Now, for this lab, all of you that are here in person will need to pick a map. Just one. One map. All of you that are taking this class online will also pick one map. I provide the digital copy to you. I have physical copies for all of you. Okay, I have them sitting over here in this room. I'll get them in a minute. Maps. There are lots of different types of maps that we use in science, in life in general, but in the case of geology, we use satellite images a lot. This is a topographic map. Each one of these squiggly lines represents a change in elevation. Using this method, we can describe changes in something 3D like elevation on a two-dimensional plane like a map. Okay? This is a geologic map. Each one of those colors represents a different type of rock from a different time period. And you can see that they all have these little abbreviations on there as well. That's a geologic map. For this lab, you are only going to be using topographic maps, though. Here's a topographic map of Odessa and Midland. It's funny, last year, when I was doing this presentation, one of my students sitting in that chair said, why is it pointing at my house? I was like, what are you talking about? I was like, your pointer is exactly where my house is. And it's like, I promise that's not intentional. He got really freaked out. But all I did was I just picked a point between Odessa and Midland and then zoomed out so I could get this image. Yeah, like he actually showed me on a map where his house was, and it's like exactly right there. It was freaky, but anyways. All right, so here we have Odessa and Midland. Where are those squiggly lines? Well, there's one right there. And notice it has numbers on it. It says 3,000. This says 3,000. Everywhere along that line is 3,000 feet above sea level. That's what a contour line is. Contour lines represent changes in elevation. 3,000 feet above sea level everywhere along that line. Okay, now let's find another line. Let's see, where's the convenient one? Right here. Here's a line. Here's a squiggly line right there. What does that say? 2,800. So between this point on that line and this point on that line, what is our elevation change? 200 feet. Between that line and that line, we have lost 200 feet of elevation. That's how topographic maps work. Okay? This is Earthquake Lake in Montana. In 1959, there was a 7.5 earthquake that caused half of this valley to collapse, cutting off the river and creating a lake. It was a catastrophe and a threat to the communities upstream. The lake began filling in the valley, moving further and further upstream, and it threatened several communities that were upstream. So the Army Corps of Engineers had to go in ASAP and blast a route through this landslide so that the river had an outlet and it would stop flooding the valley. There was still a lake there, but it didn't threaten those communities anymore. So here we have our landslide and our two sides of the valley. Let's look at this from the top down topographically. Valley, valley side, lake, landslide. And then down here, a very flat area, which is going to be this area right there, okay? How do I know it's flat?
Oh, because the lines are farther apart.
Yeah, if each line represents a change in elevation, then the further apart my lines are, what does that mean?
Flat.
A flatter area. And the closer my lines are together, steeper area. Bingo. So you are going to be getting a couple of assignments from your maps today. Okay, there are going to be a few things that we're doing. Oh, preempted me there. You are going to be learning how to read maps using the contours, but also I'm going to teach you how to find locations on maps. Being able to find a location of a thing on a map is very important, not just in geology, but in life in general. And I'm going to teach you two methods that we use for that. They are both grid systems. Do you know what a grid system is? Yeah? You basically divide the world into squares, and each square has a designation, and you tell me the designation, and I know where to find that square. Grid system. You ever play Battleship? You know that game Battleship? Right? B5. Okay, well, I'm going to go to the row B in the column 5. Okay, right there. Oh, you sunk my patrol boat. Right? Same concept. A little more complicated than that. So, we're going to start with township and range, and then we're going to move into universal transverse Mercator. Both of those are grid systems. Highly recommend taking notes on this. Just saying. This is going to be your lab. Township and range. Somebody tell me where that dot is. Let's say that dot represents my car keys. I lost my car keys. I cannot go home. Help me, students. That dot is a tracker I put on my car keys. Where are my keys?
A11.
A11. Interesting. Why are you saying A11?
Are we looking at that from a top down?
Are you? Let's assume north is up. Where are my car keys? Can you tell me? Okay, they are somewhere in the southwest of this map. That's really all you can tell me, isn't it? You have no idea of scale. There is no reference other than the fact that north is up. All right, so what do we need? We need a grid system. Hold on a second. Hey, can we keep it down? College, not an amusement park, right? Thank you. All right. So we need a grid system. I'm going to place squares on this map. And I'm going to give each row and column a designation, like A11 for battleship, like you were just saying, right? These are called townships and ranges. Townships are my rows. Ranges are my columns. Even though I've given them a designation, I need to have a starting point. Somewhere there needs to be a point of reference. I need to have a zero line. So for my townships, it is called my baseline. Okay, this represents 0 for my rows. Then for my ranges, my columns, our 0 line is called the principal meridian. That represents 0 this way. Now, since north is up, everything above my baseline is going to be township something north. Township 1 north, township 2 north, township 3 north, township 4 north. Each row counting up. Make sense? Everything below that is going to be south. Township 1 south, township 2 south, township 3 south, so on and so forth. Then on my columns, everything to the right, or excuse me, to the left or west of the 0 line is going to be range 1 west, range 2 west, range 3 west. And then on the other side, range 1 east, 2 east, 3 east, so on and so forth. And just like that, using only 2 designations, you can tell me far more detail about where my car keys are. Someone tell me where my car keys are now.
Township 2 south.
Township 2 south,
Range 3 west.
range 3 west. And if you just tell me that much, I know I have this much area to search, right? However, here's the kicker. Each township and range is 6 miles to a side. Yeah, so this is helpful, but I still have a 36 square mile area to look for my car keys in. I got that. You're not going to help me? What if I offer extra credit?
5%.
5%? Would you help me search a 36 square mile area for my car keys for 5% extra credit? How would I lose my car keys like that? Let's say my 5-year-old went throws it miles away. My 5-year-old is Superman. He landed in an asteroid last couple of years ago. Okay. What do we need?
A smaller map. Or a bigger map.
We don't need a bigger map. We need more definition. We need more data. I used to work with an Indian guy at the gold mine. His answer to everything, I was like, hey, what do you think of this? He was like, you need more data. It was so funny. That was his answer to literally everything. More data. So that's I think of him every time I say that phrase, okay? We need more data though, okay? So we take this 36 square mile area, Township 2 South, Range 3 West, and I am going to expand it. What you're about to look at is no longer this. It is this square expanded outward, okay? This is Township 2 South, Range 3 West. And I have cut it apart. I have sliced it into what? Squares, grids. We are taking our grid system and refining it down. We are adding more definition. Into how many sections?
36.
36. How big do you think these sections are? 1 mile by 1 mile. Bingo. So I have taken my Township 2 South, Range 3 West, and I have added more definition. What section are my car keys in? 30. Okay. They're in section 30 of Township 2 South, Range 3 West. That's a 1 mile square area I can search now. Much more achievable. But still too much work. So what am I going to do?
Make it again. Have another map.
I'm going to add even more definition. I'm going to take section 30 and expand it out, and I'm going to break it down into quarters. This is section 30. Just section 30. And I've broken it down into quarters, which means that you can tell me which quarter it's in. Which quarter is it in? Well, that's northwest and that's southwest. Which quarter is it in? Southwest. That's a half mile by half mile area. What if I want to break it down even more? I can take this quarter and break it into quarters. Which sub-quarter is it in?
3, 2.
Well, these aren't given numbers. They are northwest, southwest, east, or northeast, southeast. Which one is it in? Southwest again. It is in the southwest quarter of the southwest quarter of section 30, Township 2 South, Range 3 West. That is township and range. Easy, right?
This takes time, but
Right.
relatively simple.
So when we write this, we always start with the smallest area. Okay? This is a quarter mile by quarter mile area. Inside of a half mile by half mile area. Inside of a mile by mile area. Inside of a 36 by 36 mile area. Or a 6 mile by 6 mile area. Okay? All right. Now I have good news for you. On your lab, you only have to go as far as township and range. You don't need to tell me section or quarters.
But
There's no but. That's literally it. You only have to give me the township and range, no sections or quarters, because you can't zoom in on it deep with enough detail to tell me.
I think your keys got smaller in that picture.
They did. I'm trying to show you.
I was gonna use
What?
He's
these
strong.
keys that you use to mark them around like this.
No, we're not going to be using those. You'll see when you open the lab. Any questions about township and range? Okay, well then let's talk about the other grid system. UTM, Universal Transverse Mercator. Now, where township and range, we use a grid system that we kind of gave an arbitrary name to, okay? This UTM goes in meter designations, okay? So how far east or west from your zero line in meters, how far north and south from your horizontal zero line in meters are you, okay? So this is a blow up on the sides of that earthquake lake map we looked at earlier, okay? It's in UTM. This line right here has a number above it. It says 61,000 meters east. What does that mean? Everywhere along this line is 61,000 meters east of my zero line. My zero line is 61,000 meters that way. Okay, from everywhere along that line. Now, the next one we have marked says 63. Normally, these maps will only give you the whole number once, and they'll only give you the relevant numbers afterwards. So if that's 61,000 and this says 63, we can assume this means what? 63,000. Exactly. 63,000 meters east, 64, 65, 66. Now, we're missing one for here, but that's only because there was other text here that they needed to include. But we can safely assume that this is 62,000 meters east. Exactly. So this is our 61,000 meter box, 62, 63. Why am I saying that these columns are representative of those? Because right here, starting on that line, is 63,000 meters. One more meter this way, 63,001, 63,002, 63,003. Between this line and this line, all of this is 63,000 and something meters. Only here do we reach 64,000. So this column, you are only going to refer to that as 63. This is 62. This is 61. This, even though it's off the map, is still 60,000 meters east. Okay, same thing for our rows. Right here, 66, 67, 68. And up there somewhere, probably not very far off the edge of our map, 69. So if I asked you for the location of a thing using UTM, you will still only give me two numbers. It won't be township and range, but it will be X meters north or south and X meters east or west. And that's it. That's it. Grid systems. They're beautiful. They're simple. Any questions?
Is that why, I guess?
Where's the zero line?
The zero lines.
Zero line is 60-something thousand meters that way. And zero line here is 60-something thousand meters that way. These are north. These are east. These whole numbers are always at the corner of your map, by the way. If you ever look in and you're like, okay, there's my UTM number. I don't know if I'm north, south, or east or west. I'm going to go to the corner and I'm going to see, okay, these numbers are east. Okay, these numbers are north. Okay. Okay. Now let's talk a little bit more about contours. Contours being those lines that designate, or that represent, I should say, elevation change. Okay. As you pointed out earlier, the closer they are together, the steeper the slope is. The contour interval is the space between these lines. This one says 9,600. This one says 9,800. How many big separations are there? 1, 2, 3, 4. Thick lines between those two numbers. which means that between each thick line is how much elevation change. Between this and this was 200, so between each of these other thick lines must be how much? 50. 50 feet, 50 feet, 50 feet, 50 feet. Which means how much must there be between these thinner lines? 1, 2, 3, 4, 5. 10 feet.
Oh, goodness.
It's actually really easy to read if you
Yeah.
look into it.
Yeah. And you have magnifying glasses in your kits if you have a hard time seeing them on the hard copies.
I hope I don't use magnifying glasses.
I remember doing these maps in 8th grade science.
In
Yeah,
8th grade science? Very nice. Okay. Now, if I take the same box and I put it at different parts of my map, right here, this box includes 19 contour lines. This box represents or has 9 contour lines in it. They are both the same horizontal distance. What's changing?
Elevation.
Vertical distance, represented by elevation, right? This slope is nearly twice that slope because it has almost twice as many contours in the same area. Here's another note. Because we live in America and we are silly people and we use the imperial system for measurements, we have feet, miles, inches, yada, yada. It's called the imperial system. Pretty much everyone else in the world uses the metric system. Science uses the metric system, right? So ocean, being international, uses the metric system as well, which means that if your map includes any ocean on it and a question on the lab is relevant to the elevations in the ocean, you need to use meters for that. And if there's anything that includes both ocean and land measurements, you will need to convert between feet and meters.
US.
Yes, yay for the US. I do give you the conversion for that on the lab, by the way. Okay? So it's there. All you have to do is the math. So this is just showing you how your closer the intervals are, the steeper it is, right? Like right there. And the further they are apart, the gentler the slope is. On your maps, if you ever see contour lines doing a weird V shape, that means that there is a body of water there, a stream specifically, or a river. Why? Because of the nature of running water, weathering its way through the rock around it, the elevation contour intervals of this V-shaped valley are going to be V-shaped from the top down, because your stream is causing that local part of the area to reach lower elevations before the rest of it does. Okay, so a V shape represents a stream or a river. So here's a test. Where does Dead Man Creek start? Well, first we have to figure out where Dead Man Creek is, don't we? So we're going to look for it. Okay, there's Dead Man Creek. Now, how do I figure out what direction it's coming from? Follow the V shapes. It's going to V in the direction that the water is coming from. Okay, so V, we're following these V shapes. You see these V shapes here? We're following these V shapes, and here, V shapes dead end. Also, on these maps, wherever a stream or a river is starting, wherever the source is from, they make the line dotted. That blue line becomes dotted. Okay, so right here, right there, that is where Dead Man Creek starts. But now you got to tell me where that is. How are you going to do that?
The coordinates on the sides.
Uh-huh. What do we call those? What grid system are we using for this?
The
UTM, exactly. Okay, so someone tell me my UTM coordinates.
You can't really read.
Okay. That says 68,000 meters north. That says 67,000. So I'm in which row?
67.
67 ends here.
Also 66.
We are in the 68,000 meters north row, right? What column are we in? 61, 62, 63. We are in the 62,000 meters east column. So all you have to do is tell me 68,000 meters north, 62,000 meters east, and I know to look in this square for whatever you're talking about. Clear? Sweet. Now, the maps you can choose from for this, Monterey, California, and Hoquiam, Washington. I'll hand out hard copies of those in a minute. But for my online students, in the lab resources folder, you have HD, like the best definition I could get of these maps. And I highly recommend downloading them. You'll get better image quality if you download them, even if it takes a while, than you will if you just try and open these in the browser. Okay, you will want to zoom in on some of these to see those little numbers. So you'll want the best image quality possible. Please download them. Okay, if you have any questions, please feel free to reach out to me over email. We can have tutoring as long as you need it. I'm going to end the recording here.